I'm in the process of debugging a Philips plasma television. This is based on a Hitachi Fujitsu plasma panel, quite an old plasma panel. The fault with this one is unrelated to the plasma drive electronics. In this case it's with the power supply. But I thought it was a good opportunity to show how to trigger an oscilloscope on the waveform. So at the moment you can see the trigger's quite unstable. So what you basically got to do is set it up so you can get one whole subfield. And you set the trigger quite high so you catch the reset pulse. The reset pulse is this slow ramp up. And then you go into the menu, set up. This is on a Rigel oscilloscope. It applies to other oscilloscopes too. Take a little single shot here and we see that it's about 2 divisions between the subfields. 5 millisecond division, it's 10 millisecond sustain, which means it's refreshing the panel 100 times a second, and and there are, it looks to be 7 subfields in each one, so technically this is a 700 subfield per second display, which is an odd number of subfields. We normally go with 8, but I suppose it's probably using an uneven subfield widths. Anyway, let's just set this up for 10 millisecond or so hold. We want to set it for slightly more than 10 milliseconds. So 11 milliseconds. And the trick basically is getting, right, there you go. So now you've triggered on the wave. So you can turn the alternate trigger on. You can then zoom in. You can't turn the normal one on without interfering with the hold off. So if you zoom in, you'll have to adjust the hold off because the oscilloscope's triggering characteristics change. There you go. So 15 milliseconds. Hold off is a bit of an odd control on the oscilloscope. But there you can see the drive waveform going to the plasma screen. This is no picture going into it, it's just a black screen. It's a bit unstable. Sometimes altering that can help stabilize it. Of course, single shot is always an option. Go into acquire, turn memory depth onto long, do a capture. Again, because you've triggered the triggering has changed, you're going to have to alter one control this to get a stable trigger. Let's see, there we go, stable trigger there. So then you can zoom out, scroll a little. Fun. And then run stop, and you can zoom in and inspect the waveform very accurately. You even get these sustained periods there. So in a plasma television, plasma display panel, you have several periods of the sustained waveform. You have the reset or initialization pulse, which you can see here peaks up to 312 volts, very high voltage plasma displays. And this is what do they call it? Teres driver. And a Teres driver uses plus minus 82 volt instead of a single 164 volt supply. It's an interesting design. It reduces the cost of the MOSFETs but greatly increases the board complexity. So you don't see any other manufacturers other than Hitachi Fujitsu doing it. They've also got a patent on it. That's probably an important factor. But they don't make plasma displays anymore, so I believe Panasonic have that patent, but they haven't used it because all plasma displays nowadays use a 180 to 210 volt sustained voltage. Some of the older ones could get away as little as 165 or so, but this one's using a 160 volt, also 164 volt sustained voltage, which is a very low end. Anyway, so I digress. You've got the reset, and you've got the first sustain, a single sustain, 100 volt there, so well, it's a bit inaccurate, but that's minus 100 plus 100, so it's probably plus 83 volt. So by resetting it, you get this little blank period here, and the panel is then addressed. So basically, everything on the screen, all the data is loaded onto the plasma panel. So you select each line one by one by grounding it, and then you load data from the bottom of the panel, so the address CRFs, COFs. And by loading a single bit image onto the panel, you can then sustain it, which is this period here, and the sustain process, which basically means moving the voltage through from minus 100 to plus 100 on one side, and plus 100 to minus 100 on the other side. The plasma panel experiences a cell voltage change, and this change in cell voltage induces a current, which induces a light emission. So that's a single sustained field, so that's the least significant bit of the panel. We look here, I'm not quite sure what they are. There might be some kind of reset. I've never seen that before on a plasma display. They do two arrays periods here, two arrays and initialization periods here, and another single sustained. So what this probably is a least significant bit, because this is kind of like a very weak light emission from the panel. So it gives them extra resolution in the low levels. And then here, yeah, this is obviously some kind of sustaining going on. I'm not quite sure why it's before the reset period, though. I haven't not seen that before. More sustained periods, and there's a very long sustained period there. When we zoom out even more, we got an even longer sustained period. So in this one, they appear to do the resetting at the end of the subfield, which is a little odd. But everyone's different. Every manufacturer does it differently. So there's a very long one, and then the cycle repeats. And basically, they've got how many reset periods? You got 1, 2, 3, 4, 5, 6, 7 reset periods. So it's a 7-bit driven plasma panel, whereas Panasonic nowadays is using 10-bit driven, but they only update the screen 60 times a second. So you get a 600 Hz subfield drive, which is not the same as a 600 Hz LCD. It's the same as a 60 Hz LCD, but it will have motion performance much better than any LCD, because each sustained period basically lights up the panel instantly. So that's a little digression on how a plasma panel works. Enjoy the engineering porn here, because look at that. Jeez, a lot of power electronics on there. This thing is dealing with 100 volt at about 2 amps. Well, each side deals with about 100 volt, 2 amps. It's very good construction. You've got United Chemical capacitors throughout. Power supply is Philips. Now this is the faulty part, but it's got Rubicon and Nishikon capacitors throughout it. The build quality is very good. This thing here, this is an EMI shield, because these older plasma panels produce a metric fuck ton of radio frequency interference, and even with the that metal plate there goes on the back of it to create a shielded cage to keep the noise out, because you've got these inductors over there and some over there which form part of the energy recovery circuit, and you're pumping plus or minus 100 amps into the panel during the sustained process. I mean, it's not continuous, of course, but it's very brief pulses of current, because it's plasma emission. It requires it to work. You can't really make a plasma display work with low current. You get insufficient ignition. Basically, pixels don't all light up. You get some lighting up and others won't light up. The other build quality, it's got very high capacitance. You'll be very careful. I mean, this is only 83 volts, which will probably still kill you, but it's not half as bad as a 200 volt sustained. So just be very careful. You know, don't touch it while it's running, because you will kill yourself. And that sucks, because life is a kind of pleasant thing. Let's see how it's going now. What I can do is I can try and just adjust this hold off a little more. Yeah, there we go, that works. And then what I'll do is I'll turn it off, so we'll see it shut down. Not that exciting, and turn it back on. Nothing to write home about. If I extend the size and I'll then position it over there where you can see it shut down. And so what we see, the shutdown process is obviously microprocessor controlled. Look, the fantastic resolution on this thing. So what we see here basically is the sustained voltage begins collapsing, and once you get below about 10 volt, the normal sustained voltage, you basically get no light emission from the plasma panel, or very little. You might get the occasional pixel, and so the current basically falls off very rapidly. And so generally, it just, what dies first is not the sustained voltage, but the main board, because it loses power. All the other logic loses power before that. I've worked on a 50-inch Pioneer, which will cut out. The VSUS will drop to about 130 volt. You can see a few pixels sparkling, but then it will just cut off because it just can't sustain the panel anymore. So that's been an interesting introduction into plasma panels and how to use an oscilloscope to measure them. Oh, one final thing I forgot about. Since this is a 300 volt scope, I'm using a 10x probe, which is 400 volt rated. You must use a high voltage probe. A 10x is essential. You'll blow the scope up if